proceed with lecture 22, in which this will be the second part of a time varying field, in which we're going to learn about this concept here, which is a displacement current. Yeah, and then following that, we're going to learn about the Maxwell's equation for the time varying field. So we're going to summarize the Maxwell's equation for the time varying field. And finally, we're going to understand the meaning or the concept of Lossy Dielectrics, in which I've touched this a bit in the first slide just now. So we're going to discuss this in detail in this lecture 22. Yeah. So reference for this lecture 22, you can obtain it from Sadiku, page of 439 to page of 446. Okay, so these are the objectives for this lecture 22. The first one, I'm going to investigate the phenomena of displacement current. Yeah, displacement current due to time varying electric field. Okay, so this is the things that you have to understand. Yeah, you can sense something here, in which it seems to us that displacement current is originated from what? Displacement current is originated from the time varying electric field, and you did mention here phenomena of displacement current, which is due to time varying electric field. Okay, so you can see now, yeah, displacement current. Okay, number two, you're going to investigate the changes of Maxwell's equation for time varying field due to concept of displacement current, and then we're going to conclude the Maxwell's equation for the time varying altogether. Yeah, and number three, the third objective for today's lecture will be we're going to learn the concept of lossy dielectrics. I'm going to see the difference between the lossy and the lossless or perfect dielectric, and how we can use the lossy dielectrics to classify the material, whether it is a good material, a good conductor, or is it a bad conductor, or is it a good dielectric, or is it a bad dielectric. So this is how, this is what we're going to learn in this lecture 22, yeah, on the concept of lossy dielectrics and the use of it to classify the material. Yeah? Okay, so this will be the objective for lecture 22. All right, so let's have a look at these displacement current. Yeah, displacement current. Okay, so in order for us to discuss about displacement current, we need to revisit the concept of capacitor that we have learned in chapter 5 before. Yeah, capacitor. Yeah. Okay. So in this particular case, I'm using the capacitor of this structure, which is a parallel plate capacitor. Okay, so we have the current. This is connected to the outer circuit. Yeah, connected to your circuit. So that should be the supplied voltage to this particular capacitor. So basically, there should be a current flowing in these conductors, and we know that since this is conductor, so the current flowing should be the conduction current. Yeah, conduction current, I believe. Yeah, so we have learned this before. Conduction current. Conduction current basically is originated from the conduction current density, the JC. Yeah, JC, and that is equals to sigma of electric field. Yeah, sigma of electric field. Okay, so basically the IC is calculated based on the JC dot ds. Yeah, so we have learned his equation in chapter 5, relationship between the current and current density. Yeah, I and J. Right. So IC basically is the conduction current which is flowing in the conductors. Yeah, in the conductors. So that should be the case. And if we put a ammeter here, we put a ammeter here, we can see that the ammeter reading, we can have the ammeter reading because it seems to us that the current can still flow in this particular circuit. But have we ever remember, I mean, have you ever think that for this particular case, yeah, of this capacitor, we have learned previously that for the capacitor, it consists of two plates, conductor plates. One of it will be a positive charge, and another one will be negative charge, and in between it, we're going to have a dielectrics. Yeah, this will be dielectrics in between the plates. In the dielectrics, if we consider that dielectric is the perfect dielectrics, yeah, what's meant by perfect dielectrics? I mentioned this now, that the perfect dielectrics is the case whereby the sigma is equal to 0. Sigma equal to 0, which means that it does not permit the current to pass through this material. So if the sigma is 0 in this dielectric, we can see that the IC, the current in this dielectric will be equals to 0, which means that there is no such thing whereby the current can pass through this dielectric or this capacitor itself. But how can we have the ammeter reading here? Yeah, how can we have the ammeter reading here? So the concept here on how the current can pass through the dielectric, although it is a perfect dielectric, can be explained by using the concept of displacement current. Yeah, concept of displacement current. That is why, I think we have learned this in a circuit theory, right? What will happen to your capacitor when we have the source to be a DC voltage? It is capacitor. What will happen to your capacitor then? If you have a DC voltage as your supply to the capacitor, what will happen to it then? Anyone? You have learned this in circuit theory. What will happen to your capacitor when your source is a DC value, DC voltage?
Open circuit.
Open circuit. Yeah, it will be open circuit. Very good. Thank you very much, Karim, for your answer. Yeah, open circuit. Because why? So that will be explained later when we touch this concept of displacement current. Yeah. Okay then. So in order for us to explain about displacement current concept, I think it's good if we can revisit this equation that we have learned in chapter 5, which is a continuity current equation. Yeah, continuity current equation. Okay, so we can apply this equation to this particular plate. Yeah, so we have this IC, which is the current in your conductors, and basically the current that is flowing in this particular dielectric, yeah, can be explained by using this equation here. Yeah, divergence of J equals to negative D over dt rho V, in which this equation states that the divergence of the current will be actually equal to the rate of reduction of the charge. Yeah, rate of reduction of the charge. So basically, we know that the current here is actually the movement of charge. Yeah? So when the current produced, it means that the charge is said to flow in these conductors. And the charge will then accumulate on these particular plates of your capacitor. Yeah, and then we're going to explain how the current can pass through these dielectrics. So basically, when we apply this equation, it states that the current that's said to flow in this particular dielectric will be based on the rate of reduction of the charge here on your plate. Yeah, so rho V basically is the charge on the plate. So the rate of reduction of the charge on the plate will be then equals to the current that is said to flow in your dielectric. Yeah, so this is what we call as the continuity current equation, and we're going to apply that in this particular case on the plate itself. And from these equations, we have learned from the Ampere's second law, yeah, the Maxwell equation related to the Ampere's second law, which states that the curl of the H will be equal to the J. The curl of the H will be equal to J, yeah, which means that the H field is produced from the J, or the H field is produced from the current. So based on that, what we said is that J will be then substituted as the curl of H. Yeah, so divergence of the curl of H will be equal to negative D over dt of rho V. And we have learned also from the Maxwell's equation, the first Maxwell equation, which states that divergence of D equals to rho V. Yeah, the divergence, the flux equals to the charge. Yeah? The flux equals to the charge. So based on that, we have changed that the rho V will be this equation, divergence of D. Then we have divergence of the curl of H equals to this. So we can see that this relationship, yeah, because between the H and the D. But for the left-hand side, this is the identity. When we have any vectors, if the vectors is said to be curved, yeah, it's said to be curved, and subsequently we have a divergence of the results of the curl operation, it's going to have zero value. which means that for any vectors, yeah, if we have vector A, if we have divergence of the curl of A, so this value will be equal to 0. For any vectors, the operation of this divergence and the curl of the vectors, this will be equal to 0. Okay, so that should be the case, yeah? That should be the case. This is based on the identity. But we still have the value here on the right-hand side, which is negative d over dt of divergence of d. Yeah, the rate of change of your charge. Yeah, rate of change of your flux. So how can we make the left-hand side? How can we equate the left and the right-hand side? Because left is 0, but the right is not. So this is what has been done by Maxwell, yeah, by Maxwell, Mr. Maxwell. And what he did is that he tried to do the mathematical manipulation in which for this equation to be valid, what he did is that he add the right-hand side with the same terms. Yeah, so we have negative d over dt, divergence of d, so this is the case. So what he did is that he add the right-hand side with the same parameters, but this time it should be positive, right? So this value d over dt, divergence of d minus d over dt, divergence of d, so that will be equals to 0. And then we have the left and right should be equals, yeah? Both left and right will then be 0. Okay, so this is what done by Mr. Maxwell, just to verify, just to make sure that this mathematical equation is valid. Okay then, so based on this equation, we can agree just now that these equations here, negative d over dt, divergence of d basically is obtained from the first term here, which is basically equals to divergence of j. So we can then change the equation here, negative d over dt, divergence of d to be the divergence of the j. And the j here basically is your conduction current, yeah? If I can write here, j is your conduction current. Okay, so from this equation, we can then produce a very important equation. So this is done by Mr. Maxwell, yeah? So we just take the inner side of these terms, and this is all divergence, divergence of curl of H, divergence of dj over dt, divergence of j. So we just take these things here, that curl of H, we just take curl of H, we just take d over dt, and we just take j. So end up, we're going to have this equation here where we have the curl of H equals to j plus dd over the dt. Which means that if we go back to this diagram here, yeah, the j that we're going to find out here is the j inside this particular dielectrics, in which it is basically given by the curl of H. Yeah, so the curl of H is the operations to find the H field inside the dielectrics, and it is found out that the curl of H inside the dielectrics here, yeah, the curl of H inside the dielectric here in this particular dielectric, the curl of H, the value of the H field will be depending on the J plus the dd over the dt. Okay, sorry for this interruption. Okay, the j plus dd over dt. So what is meant by this? The equation here states that, yeah, before this we have this one, yeah, the curl of H equals to j. Okay, we have agreed that the H field will be produced by the current. Yeah, this is the Maxwell equation. But if you base on this equation, in this particular dielectric, it seems to us that the H field in this region or in this dielectric can be produced by two methods, by two parameters. The first one is the current, the J, and another one is the time-varying electric field, the rate of change of your time-varying electric field. Okay, so you got the concept here, yeah? I repeat again. If you base on this equation, it seems to us that the H field, the magnetic field intensity in this region, in this dielectric, it will be produced, or it can be produced by two parameters. The first one is current, or the conduction current. Second one is a time-varying electric field, because we know that D equals to epsilon of electric field. So the dD over dt is also equals to the dE over the dt. So H field in this region can be produced by the current, and it can be also produced by the time varying electric field. So based on that, that is why, yeah, we can say that the current that pass through this particular dielectric, for the case whereby your sigma equals to 0, or for the case of perfect dielectrics, remember, in which we have agreed just now that the J will also be equal to 0, yeah? When the sigma is 0, J will be 0, which means that conduction current is 0. So this was J, J is this one, which is your conduction current density. So when J equal to 0, yeah, so the current that is said to produce or that is said to exist in this dielectric will actually the current that is produced from the time varying electric field. And this current is what we call as displacement current density, or in a symbol it is called as a vector of JD. The vector of JD, displacement current density. So basically, displacement current density, the JD, is equal to the time varying electric field. So I repeat again, for the case of sigma equal to 0 in its dielectrics, the current that produced inside the dielectric here is the JD, which is the displacement current density. So for the JD to exist, yeah, for the JD to exist, your electric field, yeah, your electric field need to be a time varying. Electric field need to be a time varying. Then only we can have the JD, or we can have the the differentiation of the D with respect to T. When the D or the E is a static field, what will happen? When the E and E are static, we're going to have the case whereby the dD over dt is equal to 0, right? Because since we don't have any time varying field, E and D, the dD over dt or the dE over dt will be 0. And as such, when we have this particular case, the dD equal to 0 or the dD over dt equal to 0, it means that the JD will then equal to 0. There should be no current flowing in this dielectric. So that's what I mentioned just now. For the case of a capacitor, when we have a DC current flowing in this capacitor will happen, we are going to have an open circuit. Because why? Because no current can flow through when this current is a DC current. Yeah, because we know that DC current is a static current or static field will be produced. Yeah, so for the case of static field, there is no such case of displacement current density. Yeah, so displacement current density will exist only when you have a time varying field. Yeah, so that's why this capacitor will operate only when we have a time varying field, or in this particular case, it should be the AC current. Okay, is that clear on this explanation on the displacement current? Yeah, so in short, we can just say that displacement current JD will be equals to the time varying electric field, yeah, the dD over dt. So in your capacitor, for the case of perfect dielectric, the equations here, initially we have curl of H of J plus dD over dt. In the case of capacitor with a perfect dielectric, the equations can be reduced to only this, where we have curl of H just simply equals to the vector of JD. Okay? Okay, I hope that this you can understand this clearly on these issues. Yeah. So if based on this equation, where we have the curl of H equals to dD over dt. Okay. So this is the other case of relationship, yeah, between the time varying field and electric field, in which previously in a Faraday's law, we have learned that the curl of E, sorry for this interruption. Yeah, sorry for this interruption. Yeah, it's my mistake. I'm not sure why. And my tab here. For the previous case of Faraday's law, we have the curl of E equals to negative dB over dt, in which we have agreed that based on this equation, the time-varying electric field is produced from the changes of the time-varying magnetic field. For the case of displacement current density, we have the curl of H equals to dd over dt, which is the time-varying magnetic field. Yeah, remember, yeah, this one is the case whereby the H is time-varying. The time-varying magnetic field can be produced from the changes of the time-varying electric field. Yeah, so we can see relationship between the two equations here, Faraday's law, displacement current concept. Okay? Okay, I hope I make it clear to you on this concept of displacement current, yeah? Right, so that will be the conclusion of the things that we have learned so far from the starting of EMT up to now. So these are the things basically that we want to conclude, yeah, in EMT, which is the Maxwell equation. The first one is a static field base that we have learned previously. Divergence of D equals to rho V, divergence of B equals to 0. Yeah, this is based on the Gauss law. This is the Gauss law for magnetic field. Yeah, this is based on the chapter 4, the energy conservation. And this is based on the Ampere-Circuital law. Yeah, so two equations from the electric field, two equations from magnetostatic field. We have learned this in static field before. And we can see that in time-varying field, that will be a significant changes. For the first one and the second one, there should be no changes at all. Yeah, both are still the same. But for the third one, we're going to see that the curl of E equals to negative dB over dt, the changes which is due to the Faraday's law, yeah, FL standard Faraday's law. And the fourth equations, this is based on the concept of displacement current. Yeah, the concept of displacement current density. Yeah, we have the curl of H equals to J plus dd over dt. So these are the changes, the exact changes that we have for the case of a time-varying field as compared to the static field. Okay, then, is that clear on this explanation on the displacement current and also on the Maxwell equation for time-varying field so far? Is there any questions? Is there any questions here? No, yeah? Okay, I think we can proceed with the example related to the displacement current, just to make sure that you have understand this clearly on the concept of displacement current, yeah? Okay, in this example number 1, we are having a coaxial cable which has a dielectric of F and R equals to 4, which is a relative permittivity of 4. The inner conductor has a radius of 1 millimeter. Yeah, inner conductor has a radius of 1 millimeter, and the inside radius of the outer conductor is 5 millimeter. Okay, so let us sketch this diagram first. So we have the coaxial cable. Okay, the coaxial cable like this. Yeah. Right, that should be a coaxial cable. We have the radius inner conductor is 1 millimeter, so that should be 1 millimeter here. 1 millimeter, and the outer conductor is 5 millimeter, so we put this as 5 millimeters here. Okay. Right, and in between the two conductors, we have the permittivity, the material with epsilon equals to 4 epsilon naught, yeah, because the value is given to be relative permittivity, so we just put here that the permittivity in the dielectric here will be 4 epsilon naught, yeah. The question is, find the displacement current between the two conductors per meter length of the cable for an applied voltage of V here. Yeah, find the displacement current between the two conductors per meter length of the cable. Okay, so how to find the displacement current between two conductors? Okay, so basically, we have agreed. Yeah, we agreed in our circuit theory before. Yeah, in our circuit theory that the equation of current in a capacitor is based on the equations of I equals to C dV over dt. Am I right? So we have learned this, yeah, in your circuit theory, I believe, the equation that relates the current and the capacitance. Okay, I is equal to C over dV over dt. So basically, the I that we have here, the I that we have based on this equation, this I is your displacement current. Yeah, displacement current. So to be in short, you can say that in your capacitor, the current that we have is the displacement current, yeah, displacement current. Okay, the conduction current that we're going to have in your capacitor is the lossy current, yeah, that it will not be contributed to the capacitance, but it will contribute to the heat, yeah, contribute to the loss. So we're going to learn this later when we learn about the dielectrics, lossy dielectric later on, yeah, but we agreed here that the current that is produced in your capacitance based on this equation of C dV over dt, the R here is the displacement current. Remember in the capacitor just now, in capacitor we have two current, right? We have, I'm using this equation here, the curl of H equals to J plus dD over dt. So we have two current here. The J is your conduction current, the JC I can say, and next one is the JD, which is displacement current density. So the I that we have here basically is the JD, or in short we can just say this as the ID lah. The JC, as I mentioned just now, is not the current that will contribute to this equation of I, because the JC will be the cause of heat loss. Yeah, the cause of the heat loss. Yeah, so we're going to learn this later on. Yeah. Right, so based on this equation, since we know that the displacement current in capacitor is based on C dV over dt, so in order for us to find the displacement current ID, we can just simply use the C, capacitance value, and we need to differentiate the voltage with regard to time, because we know that for this capacitor, for this particular coaxial cable, the applied voltage is this one. That means that if you base on that, the voltage applied across the cable is the VT. Yeah, VT is the voltage applied across the cable between the inner and the outer cable. Okay, so we are given a C here, because C here is a capacitance for the case of coaxial cable. Yeah, I don't have to prove this. I think you can prove this on your own. Yeah, we have done this in our lectures in chapter 5. So we just use this equation of C, which is the capacitance for the case of coaxial cable structure. So we have 2 pi epsilon L over ln of RB over RA, in which RB is the outer radius, RA is the inner radius, and the dV over dt will be d over dt of your voltage here, which is 100 cosine of 12 pi times 10 power of 6t. Okay, so since we need to find displacement current per meter length, so I can bring L to the left hand side. So I'm going to have ID divided by L. So that would be 2 pi epsilon. Okay, 2 pi epsilon divided by ln. I can just put epsilon to be 4 epsilon naught, yeah? So that should be 4 epsilon naught, because that should be the material, permittivity of the material that we have in between the cable, in between the conductors. And ln RB over RA, which will be ln of 5. Yeah, RB is the outer, RA is the inner, so 5 over 1, yeah. So we have ln of 5, and d over dt over 100 cos 12 pi over times 10 power of 60. We're going to have 12 pi times 10 power of 6, and then that should be multiplied with the negative 100 sine of 12 pi times 10 power of 6 t. Yeah, so that should be your displacement current per meter length, which is in ampere per meter unit. Yeah, so negative basically will be the direction of it. Yeah, direction of the current. Yeah, so negative will be I can say reflected to the direction of your current in this particular case. Yeah. All right, I hope that's clear on this equation. I mean, in this solution. For example, 1, basically what I did here is that I tried to relate the concept of current or displacement current that we have learned in the previous slide, and the concept of current that we have learned in circuit theory. Yeah, based on this equation here, I of C dV over dt, and this current basically is your displacement current in your capacitor. Okay. All right. Is that clear in this? Right. So I now shall proceed with the example number 2 here. also related to displacement current density concept. Okay, so in this example number 2, we need to find the amplitude of the displacement current density. So in this particular case, need to find the amplitude of displacement current density in the air near a car antenna. In the air near a car antenna where the field strength of an FM signal is given by this. Okay, we are given that in this particular case, we have the car antenna. Say this is your car antenna. There's an E field at this particular location near the antenna, given by 8 of cosine 6.277 times 10 power of 8t minus 2.092 y direction of z. Electric field is given by this equation, which is at the location near to the antenna structure. The field strength of the E field. The field strength of the E field. The question is, you need to find the amplitude of the displacement current density related to this particular electric field E. Okay, so we have learned that from our discussion before that the displacement current density JD is equals to the time varying changes. The changes of your time varying electric field density or intensity. So that's the relationship, displacement current and the electric field. So if based on this equation, we can know that since we are given the E field, since we are given the E field, so we can then differentiate this particular E field, in which that will be then going to find the JD, which will be the differentiation of the DD with regard to time. So you're going to have, and this is the air, in the air, so you're going to have that the air will be epsilon naught the permittivity, and that should be the d over dt of the E field. Okay, and from here we can differentiate the E field here straight away, and we're going to have that should be 8 multiplied with 6.277 times 10, sorry for this interruption. Okay, 6.277 times 10 to the power of 8. Okay, and then we have negative, we are supposed negative here, right? Because negative cos here. A sine of 6.277 times 10 power of 8 t minus 2.092 y direction of z. Okay, if you base on that, your JD will be based on this equation, But since we need to just find the amplitude of it, so the amplitude of the JD will be simply this value, which will be epsilon naught multiplied with 8 multiplied with 6.277 times 10 power 8 ampere per meter. So that should be the amplitude of the displacement current density. So based on this example, it can be said basically the current in this particular case, displacement current basically is in terms of the wave. The current is basically in terms of wave. Okay, this is the origin of the wave that we have in our environment. The wave propagation. The wave propagation basically is the time varying electric field, because evidently it shows based on the concept of capacitor, right? Capacitor that we have learned before, that in between this plate of a capacitor, there is a current JD, which is based on the DD over DT, which means that this is not a conductive material. It will not conduct any current to pass through, but still the current can pass through, which is the current is in terms of the time varying electric field. So this happens. This is what we can say about the wave propagation in our real world environment, in which the wave basically is based on this concept of the time varying field. Time varying field. Okay, which is basically the wave that we have here in the real world is basically a current, displacement current to be exact. Okay, you're going to learn about wave propagation in next chapter. In next chapter, so you're going to see later on how we can apply all of these Maxwell's equation in explaining about the wave propagation later on, yeah, in our last chapter of EMT. Okay, so back to this, yeah, we go back to this example number 2. So I hope that you have understand on these issues on calculation of the displacement current, in which for us to find the displacement current density, we need to obtain the E field. We will differentiate the E field, so that will give us the displacement current value. Yeah. Okay, I proceed with second example here. Okay, for a second example, we are given again a space within a large power transformer where the H is given by this. Okay, so in this particular case, we are not given the E field, but we are given the H field, yeah, the H field intensity. So we need to find the amplitude of the displacement current density. Okay, so how to find the displacement current density based on this H field? Okay, so in this particular case, we have agreed that the equation for Maxwell is curl of H, yeah, equals to J plus dd over the dt. Yeah. Okay, so in this particular case, so if we are not given any information about the current values, yeah. So what we can say in these conditions in A space within a large power transformer, we can assume that the J or the conduction current in this problem is equal to 0. So when we have this assumption, we can then reduce the equation here to be simply the curl of H will be dd over the dt. Yeah. So basically, we can find the displacement current density by simply evaluating the curl of the H, the curl of the magnetic field intensity. So that's why I give you the curl formulations here related to the Cartesian systems of coordinate. So based on that, we can say that the JD, which is the displacement current density, can be calculated by simply evaluating the curl of the H. Okay.
Doctor, may I know why we can assume the J is equal to 0?
Okay, because in this particular example, we are not given any informations about the conductivity of the material, because in the A space, right? In the A space, so in the A space, we are not given any values of conductivity. So based on that, we can assume that conductivity equal to 0 in the A space, and as such, the J will be 0.
Okay. And just now you doctor mentioned about the in real world about the wave
propagation, yeah. Okay.
That means, can you explain again what is mean by the propagation? That means all the sound wave are the JD, is it?
Not the sound wave exactly, the electric field wave. Remember, I explained to you just now that we have this capacitor, right? We can explain that the wave, yeah, the wave can, the current can pass through this capacitor, yeah, which is although is this is a perfect dielectric, sigma equal to 0. So the signal that, the current that propagate through this perfect dielectric is given by curl of H equals to JD, JD equals to DD over the DT, which means that the current that pass through this particular perfect dielectric is it's a wave actually. It's a wave, and the wave is given by this time varying electric field. Yeah, and the same things apply in our real world because we have the wave. Yeah, we mean the air that we have here is not conductive, right? It's not conductive. So how the wave can pass through? So basically, it's based on this concept, the time varying electric field. Yeah. So when we have a case whereby the material is not conductive, yeah, in which we know that the current cannot pass through it. So there is a thing. There is the method in which the current can still pass through the medium, and the current that passes through the medium is what we call as a displacement current. And we're going to learn in next chapter that this displacement current is known to be a wave or electromagnetic wave.
Okay.
Okay,
Thank you.
all right, yeah, all right, good. Okay then, so we go back to this example. So thank you, Rehan, for your questions. Okay, we go back to this example here. Okay, so we have right. So we have to do a curl operation for the Hitch field here. So see that for this particular Hitch field, we have Hitch in the direction of Y. So this, which means that this is HY. Yeah? This is HY component. So for the HY component, if we base on this equation here, we have this differentiation and also this differentiation. So the rest can be equated to 0, yeah, because all of these are not HY, we have HX and HZ. So our interest will only be on these two terms here, which is the dHy over the dZ and dHy over the dx. And if we base on this equation of Hitch field, we have a variable of Z only. Yeah, variable of Z only, which means that there is no variable of H, variable of X. So again, this can also be cancelled out. So we can then simplify that the curl of H for this Hitch field will be negative dHy over dZ, direction of X, straight away. Yeah, we can simplify it further like this. So our task is just to differentiate the dH or the H field with regard to Z. So we're going to have what? We're going to have negative 10 to the power of 6 multiply with 1.2566 times 10 to the power of negative 6. Yeah, and then we have negative sign. Yeah, negative sign. Okay, negative sign of 377t plus 1.2566 times 10 to the power of negative 6 Z, yeah, in the x direction. Okay, so that should be your, correct. So that should be your JD, yeah, that should be your JD. Based on this curl operation of the H, yeah, right? And based on that, since we need to find the magnitude only, so the JD magnitude that we need to write here is based on these equations only. Yeah, because negative and negative is positive, so we just have 10 to the power of 6 multiply with 1.2566 times 10 to the power of negative 6. So that should be your magnitude of your displacement current. Yeah, magnitude of displacement current density. Okay, is that clear on this example number 2? Okay, yeah, so I hope that's clear then. In this example number 2, I give you two different methods on calculation of the displacement current density. The first one is through the direct method, which is just a differentiation of the dd over dt. So that would be for the first case. But for the second case, since we are given the H only, so we need to find the curl of the H field, then only you can obtain your displacement current density value. Yeah, so this is the methods that can be used to calculate the displacement current density depending on the information given in your problems. Yeah. Okay, so let us have a look at this example number 3. So example number 3, we are given the question whereby find the amplitude of a displacement current density in a metallic conductor at 60 Hertz if epsilon of epsilon naught, mu of mu naught, sigma is given, and J is sine 377t minus 117.1 Z in the direction of X. Okay, so we need to find the displacement current density in this particular case. Yeah, so we are given that this example number 3, this problem is related to the metallic conductors at 60 Hertz. We have the following parameters: the permittivity, the permeability, and the conductivity. And we are given the J straight away. Okay, so we can agree that since this is related to the conductors, so the J that we have here will be the conduction current. Yeah, this will be a conduction current because we are dealing with the metallic conductors. Yeah, so the J that we have here will be a conduction current, in which basically that J will be equals to the sigma of the electric field E. Yeah, the sigma of electric field E. But you need to find what? Need to find the amplitude of displacement current density. So in order for us to find the displacement current density, the JD, you need to find the E field. You need to find the E field so that when you have the E field, you can differentiate the E field value and then you can find the JD. Okay, so based on this motivation, what you have to do that based on this equation of J equals sigma of E, you need to find the electric field first. Yeah, you need to find the electric field intensity that is said to exist in this material. And from this electric field that you can calculated, you can then use it to find the JD, which is based on the differentiation of the E field with regard to time. So that's how we find the GD magnitude. Okay, back to this. So we need to find the E field then. So E field will be simply J vector over the conductivity. So we have J of sine 377t minus 117.1 Z divided by the sigma, which is 5.8 times 10 power of 7. So we can have it as 1.1 over 5.8, and that should be 10 power of negative 7 straight away. And then we have sine, sine of 377t minus 117.1 Z direction of x. So that should be my E field. Yeah, that should be my E field, which is in megavolt per meter unit. Yeah, because the J is in mega ampere per meter squared. Yeah, so from this relationship, we can find the E field straight away by simply have a ratio between the J and also the sigma, the conductivity, and that should be the E field. And from this, we can find the JD straight away. JD will be simply dd over dt, which will be epsilon naught, because we have learned that the permittivity is just epsilon naught only. So we have epsilon naught and we have d over dt of the E field, which will be d over dt of 10 negative 7 over 5.8 sine of 377t. Sorry, need to erase this. 377t, okay, minus 117.1 Z direction of x. Okay, so when we differentiate with regard to time, with regard to time, we're going to have epsilon naught, 10 power of 7, 5.8 multiplied with 377. That should be cosine of 377t, minus 117.1 Z direction of x. Okay, so that should be your JD, which is the displacement current density in the units of mega ampere per meter squared. So that should be your displacement current density, and the magnitude of it will be this one. So that should be the amplitude. So the JD amplitude will be simply epsilon naught 10 power of 7 over 5.8 multiplied with 377. So that should be the amplitude for your displacement current density. So I think that should be straightforward problems. We just need to find the E field, and from the E field then only you can find the displacement current density. Okay, is that clear on this example number 3? Okay, hopefully I make it clear to you on this concept. So I think we can just proceed with example number 4 here. On this, this is based on the previous final exam questions. We are given a case of parallel plate capacitor of plate area S uses field with a perfect homogeneous dielectric of permittivity epsilon. Okay, so we have a parallel plate capacitor. The distance between the plates D is much lesser than the dimension of the plates, so the fringing effects can be neglected. The capacitor is connected to a slowly time-varying voltage Vt, which is V0 of cosine omega t. The question is find the displacement current density in the dielectrics and the total current through the capacitor terminals. Okay, so if we base on this, if I can sketch a diagram for you, that should be your capacitor plate, is connected to this conductor here. capacitor plate. The area for this capacitor is S, that should be the area. And the distance between the plate is D, is given here to be the D, the distance between the plates. And it's assumed that the D is very much lesser as compared to the dimension of the plate, which means that the D is much lesser as compared to the S. Yeah? D is lesser as compared to the S, the area of the plate. So the capacitor is connected to a slowly time varying voltage Vt, which is V naught cos omega naught t. So it's connected to a time varying source, which is Vt. Vt is V naught cosine of omega t. Yeah. Okay. So based on this, we need to find the displacement current density in the dielectric. So what should be your displacement current density in dielectric? So we're given here that the dielectric in here is filled with a perfect homogeneous dielectrics of permittivity epsilon. So when we say the perfect dielectric, it means that this is a case of lossless. Lossless means there should be no values of conductivity. Sigma is 0. That's what we call as a perfect dielectric, in which it does not permit the conduction current to pass through it. That's why the sigma is 0. Yeah? And then we are given that the permittivity is given to be epsilon only, just given in terms of a symbol. So that should be the properties of your dielectric here in your capacitor structure. So the question is find the displacement current density in dielectric. So we know that from our discussion before, from the curl of H equals to J plus dd over dt in your dielectrics, in this dielectrics. And we have agreed based on this diagram that J is 0. There should be no conduction current. So the equation has been now reduced to the curl of H equals to dd over dt. In which we can say that based on that, the displacement current density, the JD, the JD, which is your displacement current density, shall be then equals to the time rate of the rate of change of your D, the D, in which we can also write this as the d over dt of epsilon of E field. Because we know that this dd over dt is the time varying field inside your dielectrics, in between the plates. So the dd over dt, if I can repeat it for you, the dd over dt here is a time, is a rate, is a rate of change of your electric field intensity in this material. Okay, so if we can work on this, you're going to have JD will be equals to epsilon dE over the dt, dE over the dt. Okay, we need to find relationship between the E and the V. Relationship between the E and the V. And we have learned this from our discussion in chapter 4, that because we know that from this equation we cannot have the E field. We're not given the E field. So, but we are given the VT, the potential between the plates. So what we can do is that we can use the information of VT to find the E field, and this can be based on the equation in chapter 4, whereby V equals to integration or negative integrations of E dot dl. We have learned this basically in our lectures last time, in chapter 4. And if you base on this particular distance between the plates, we know that the plate is having a distance of d, distance of d. So we can say that if we want to find the voltage difference between between the two plates, it should be based on the E dot dl, in which the range of E field or the range of dl should be from 0 to d. And as such, if we proceed with that, we're going to have that the E shall be based on the equations of V divided by D. So that should be the relationship between the E, the V, and the distance between the plates. So based on that, you can have the V, which is given to be V naught cos omega t. So we have this as V naught cosine of omega t divided by D. So we can then bring this down here, because based on this equation, we have successfully obtained the E field in terms of the V and also in terms of the distance D between the plates. So we need to differentiate the E field with regard to time, and as such, you're going to have that this will be, this will be epsilon. You need to substitute with this equation here, epsilon over D, over D, this is over D. the d over the dt of the Vt, yeah, and that will be epsilon over d times omega times the V naught of sine omega t. That should be my JD. Yeah, because we have a differentiation of, sorry, this is over dt, yeah, differentiation of Vt with regard to time. So when we differentiate this particular Vt with regard to time, we're going to have V naught omega sine omega t. Yeah, V naught omega sine omega t. So based on that, we can say that your displacement current density, the JD, yeah, the JD will be equals to epsilon over the d omega V naught sine omega t. So this is the JD, the magnitude of it. Yeah, we're not sure about the direction. Yeah, because in terms of the vector, we're not given any information about the vector. So we just take the magnitude of it. So the JD magnitude will be simply based on what we have calculated just now, which is epsilon over d omega V naught sine of omega t. Yeah, so that's how we calculate the JD. So what I want to inform here is that we need to use the information that we have learned from the previous chapters, yeah, from chapter 4, from chapter 3, in which if we base on what I did here, yeah, since in this particular case, if you need to find the JD, you don't have the E field, the exact E field in these questions, right? So we need to find the E field based on the given information. So what I did is that I'm using the equation or informations of potential. Yeah, so I'm using this equation here, V of negative E dot dl, and from this equation we have come out that E and the V shall be integrated by this equation here. V will be V over D, whereby D is the distance between the plate, and from here I can obtain the E field to be V naught cos omega t over D, and that shall be then used to find the JD, yeah, which will be the differentiation of the E field. Okay, I hope it's clear, yeah, on this example number 4, part 1, on finding the displacement current density in dielectrics. Okay, number 2 is to find the total current through the capacitor terminals. Yeah, so I think that should be no problem at all, because we have learned just now that in this particular case, the current, yeah, is based on this equation here. We don't have any conduction current across the capacitor. We only have the displacement current density. So you can find that the total current, I can put here a total current, I total shall be your ID, which is your displacement current only. Yeah, so that should be the equation where there should be no conduction current. So I total will be ID across the capacitor, and we can find that the ID shall be equals to J dot ds. Yeah, we have learned this, J dot ds here. Sorry, if I can erase certain part of this. Okay, let me erase certain part of this just to make it clear for us, for all of us. Sorry for this, yeah. Okay then, go back to this concept. We have learned that across the capacitor in this material dielectric, we have learned that there is no conduction current. Yeah, we have IC equals to 0, no conduction current. We only have displacement current ID. So for that particular case, for the question number 2, which is to find the total current through the capacitor terminals, it can be said that the total current is just consists of ID, or just consists of displacement current only. Okay, so and we have learned previously in chapter 5 relationship between the ID and relationship between the current and your current density, the I and J. We have learned in chapter 5 that I shall be integration of J dot ds. Am I right? This is your relationship. So we're going to use this again because this is your current, the ID. So in terms of the ID, it should be ID equals to integrations of JD dot ds. Yeah, JD dot ds, yeah. Displacement current will be integration of your displacement current density dot product with your surface. So in this particular case, you have successfully obtained your displacement current density magnitude, which is epsilon over d omega v naught sine of omega t. So this is the magnitude of your displacement current density. So to find the ID, simply we just need to identify which area that we need to care about. I mean, which area that we need to take here. Yeah, which area that we have to take here. So the area that we need to use here will be the area of the plate, which is the S. Yeah, area of the plate, which is the S, because this is the current. Yeah, which is this is the area that will be passed through by this particular current. Yeah, so I repeat again, the ds here, the area, we need to find out, that should be the area that will be passed through by this particular current. So in that particular case, we can simplify, or we can just ignore the integration. Simply, we just have the multiplication between the JD and the area of S straight away. Yeah, because we know that the JD and DS need to have a similar direction of unit vector. Yeah, because we have similar direction of unit vector, so the dot product can be then producing a positive value, the JD and the S. Yeah, and the S is the area of the plate, and simply from here we can find that your displacement current magnitude will be JD times S, which is epsilon omega V naught S over D sine omega t. So that should be your magnitude of your displacement current, and subsequently the magnitude of your total current through the capacitor terminals. Okay, so that should be the current that will pass through the capacitor terminals, which is solely based on your displacement current only.